So I'm very glad that we've had a previous talk on calculus, so there's a bit of a discussion on this exciting new approach in archaeological science. So my discussion and my presentation is about better understanding this dietary record. And I'm really interested in how we can evaluate and test this material using populations with known diets. So I wanted to see how we could do this with a population with a very well documented diet. So that's what I've done with this study, which uses chimpanzees from the Thai forest. So as Karen Hardy covered very comprehensively, dentocalculus or tartar is this mineralized dental plaque, and it preserves many of the characteristics that we see in plaque of recent people. It's known that this plaque and dental calculus as well seems to trap particles, particularly relating to diet as well as other aspects of life history. So this, of course, is a great deal of potential for reconstruction of ancient diets. But we know from these studies using archaeological dental calculus, as well as the studies using plaque of modern people, that the particles relating to food or life history are only a very, very small component of the dental plaque. And that's interesting because of if you consider how much food must be consumed by individuals over their entire lifetime. So why is there this discrepancy between the two? And if food entrapment in calculus is so uncommon, so stochastic, is it a representative process? What can we learn about the totality of diets using this material if it's so underrepresented in dental calculus? So there's very limited information on this topic. There have been very few studies using modern populations or using ancient archaeological populations. There have been no studies using controlled diets that could really evaluate this material for us. So I think mostly archaeological scientists have just assumed that it represents a long-term dietary average. But there's good reasons to believe that it might not necessarily be so. If we take, for example, starch grains, starch grains are a very important part of dietary reconstruction because they're so common, because starch is such a big component of many human diets. But starch, once it enters the mouth, is immediately exposed to alpha amylase, which can digest starch and hydrolyze it in a very short period of time. So from that point of view, clearly the mouth is a hostile environment for starches, as well as probably other microremains in different ways. Some researchers have gone as far as to suggest that the microremains that are reported in dental calculus studies are just contamination and have nothing to do with diet. So in this model, I guess the microremains are seen as something relating to archaeological sediments, the movement from the archaeological sediments, or from different stages during post-excavation. So we need a population that we can test diet and that will allow us to really evaluate this material in a very well-studied and controlled dietary pattern. So that's actually surprisingly difficult to do with modern populations. But one example where we can do it is chimpanzees, because chimpanzees have diets that are relatively constrained and can be studied and modeled and well understood. So for the study, we investigated whether we could examine calculus from chimpanzees to answer this question. To do that, we investigated could we use the Thai chimpanzees, because this is a group of wild chimpanzees that are quite well studied, and they have a very diverse diet which has many starchy foods as well as many phytolytic foods, mammals, birds and invertebrates. And they live in quite significant isolation, so it means that they're not consuming agricultural foods. And that's really interesting because it's only when you have this kind of entirely wild diet do you have a really good analog for ancient diets that we really need to study this material. of course, what makes this population so interesting is that it's been so well studied since the 1970s, and since about the 1992, I think we have very, very detailed behavioural records comprising over 1 million behavioural observations, and this gives us minute by minute accounts of everything that chimpanzees are doing and eating, plant by plant, minute by minute. So we really feel that these long-term dietary records are essential, because diet may vary in a population, maybe according to weather fluctuations. Certainly in this group, plant foods are very seasonal, and they vary in how important they are from year to year. So we looked at a skeletal population of this group of chimpanzees from the Ivory Coast, and that this population is curated in Leipzig, and we found that there's heavy calculus deposits in nearly every specimen. And the calculus was in relatively good condition, with only limited alteration, just with some measures to clean the skeletons to prevent any transmission of diseases that might be present in these wild groups. So with this sample in mind, we set about to build the following objectives to answer our research question. And we wanted to see if we could accurately predict diet just using calculus. To do this, we established we could first make a quick check of this by using counts and assessing if the microremain counts are increasing with the age of the individual chimpanzee. And then once we had these counts ready, we could use reference plants to identify the microremains and to see if we can predict the types of plants they're eating, and are those predictions accurate. So we examined dental calculus from 24 chimpanzees, and we found, using conventional methodology, sampling the calculus from each tooth and using an optical microscope, we found starches and phytolates in most of the samples, as well as a variety of other microremains. Some of these are beyond the scope of the study, but we also include in part of this presentation unsilified plant fragments, like just cell walls, because they're easy to quantify for this study and they're relevant for plant consumption. So we can get an overview of this data very quickly using bar charts shown here. And right, so they're sorted by each class, so like starches, phytolates, and unsilified plant remains, and of course they're also sorted by age. So this is showing the microremains per an individual, as you can see in the axis. But we can also look at it as per milligram of calculus. And this is a much more variable picture than the previous, but both show that we have predominantly phytolates in these samples, with variable amounts of starches as well, and also other microremains. One of the things that was apparent when we looked at these samples was this distinction between the youngest and the oldest chimpanzees. And although it hasn't been discussed much in past literature, I guess it's almost self-evident that the youngest individuals are not going to have as much of a history of plant consumption due to breastfeeding. So we noticed that this distinction overlapped with the documented age when weaning ceases in this group. So potentially this reflects kind of a heavy microremain accumulation instead of becoming fully committed to plant foods. Of course, we wanted to really test this as objectively as possible. So to do that, we used a negative binomial model, and we took into account different samples of different amounts of calculus and different chimpanzees or different sex. Using this approach, we could decisively show that the microremains were actually more common on older chimpanzees, meaning that they indeed represented an accumulative long-term record. Of course, we wanted to use those observational records, which were making these chimpanzees so interesting in the first place. So we went through the observational records and we identified as many plants that could be sourced and sampled on site in the Ivory Coast. And we didn't sample every plant that these chimpanzees consume, but we managed to sample all of the important plants. And from this, we went through them and looked at starches and phytolates from each plant. This is important because some plants aren't producing these microremains, and some that do are producing only very undiagnostic or very low numbers. So we identify plants that are almost certainly should be in the calculus of these chimpanzees, including 13 starch-producing plants and 7 phytolate-producing plants. As you can see, these represent a variety of different morphologies, which have different levels of distinctiveness, but we treated them the same in terms of including them in the model, so we could assess which can be distinguished and which can't be. We then, using available literature on microremain classification, we developed 15 variables that could capture the variation in surface, size and shape variability. And we collected these variable data on these reference plants. Using that data, we could build an identification model using an ensemble of classification trees. With a subset of that data, which we hadn't used previously, we could assess the reliability of this classification. Doing it at genus level, we could quickly see that some plant genera were easy to classify, while some were much more difficult. They vary from 94% to as low as 22%. And this matched our expectations about how likely these microremains were to be classified based on initial open examination of the microremains. We then did the same procedure for the microremains actually in the calculus, and this allowed us to generate a predicted plant of origin. We can look at these results as a dietary profile. Here is just such a dietary profile based on phytolate data alone. You can see a certain pattern in different samples, but there's a lot of variation. We can look at the same dietary profile using just starches in this graph, and this shows a much more variable picture, reflecting the fact that starches are much less common and are occurring in much smaller numbers, of course, but also that the starches were actually more difficult to classify morphologically. So to compare this to the actual diet of these chimpanzees, we used donuts to quickly assess how the two dietary records matched. We could quickly see, if you could see the outer ring represents the overall diet of the Thai chimpanzee population, while the inner one represents the summed diet predicted of the 24 chimpanzees. So for the phytolates, it was a pretty impressive match. But with phytolates, it was a different picture altogether. And this matched the expectations based on the fact that starch is much less common and are much more subject to degradation than phytolates. Although the starch donut is not matching the actual diet of these chimpanzees, you can still see there's a lot of plants present in some comparable proportions to their actual diet. So to really assess finally the relationship between the microremains in the calculus and the actual diet based on these long-term dietary records, we used random effects models, and we took into account all the sorts of confounding effects that could influence the status, such as the fact that some plants are much more difficult to classify than others. Using this approach, we found that indeed the phytolates predicted diet well, while starches did not do so. So, in summary, I think it's safe to take the following message home, that dental calculus can indeed reflect diet, and we can learn a great deal about diet from dental calculus, but it's a varied picture and it's subject to all sorts of preservation issues. Both starches and phytolates are a very important part of reconstructing diets from dental calculus, and there's many lessons to be learned using these microremains. Of course, the starch dietary record is far more stochastic, so it doesn't seem to ingrain the proportionality of that might be expected, like what you would see in phytolates. We also noted that indeed calculus seems to be able to potentially reflect some data on weaning, but this requires further investigation. But it's something that should be considered in any future studies that use younger individuals, as well as potentially being a subject of its own to learn more about weaning in past populations. So, so this is my acknowledgements, and just thank you very much.
Questions?
Hi, Robert. Just a question. I don't know, I might have missed this, but when you were doing your cumulative effect from infants up to adults, presumably you used exactly the same size of calculus sample for all your testing.
So what we did was we weighed the samples by the milligram, how many milligrams the samples were.
So you weighted,
we weighted it.
You weighted your results against that.
And of course, the youngest chimpanzees we sampled only permanent dentition.
But you took that into consideration when you were weighting your samples.
Of course, yeah, and with both models.
Okay. More questions?
Do you get any dental calculus on the deciduous teeth?
Yeah, I suspect so, but there wasn't a lot available in the population, so it's kind of difficult to kind of give a very conclusive answer. I would definitely say that it's less common than in older specimens. So permanent dentition has more than deciduous dentition.
Anything else? Okay.
Sure.
Sorry, I would just like to say that I actually pulled out one of my slides because I didn't have time to put it on, but I have a micro CT scan which actually shows how dental calculus develops horizontally in layers all the way through, and so it's a shame I had to take that slide out, but that shows very, very clearly how it accumulates over time as the individual grows.
That'd be very interesting to look at, definitely. Excellent.
Sorry, I can send it to you.
Okay. Anything else? Or?
Or? No. Thank you.